Okay, welcome everybody to the last talk for this term in Po. It's our pleasure to have today Ioana Dumitriu from University of California in San Diego, who will speak to us about spectral gap in regular graphs and hypergraphs. Thank you.
Thank you very much for inviting me. It's great to address a diverse audience. I'm going to go relatively slowly and define all the quantities that I'm going to talk about. I would like to also note that you have had in the past two speakers whose names will appear as references in my talk. It was great to see that you've already been exposed to their names. Sadly, they, as I checked, they didn't talk about any of the issues that I will be mentioning them for in my talk. So I think that my talk is probably going to introduce some new notions to most of the audience, which is why I'm going to try and go slowly. Okay, so this is a talk that relates to work that I've done with Herandi Brito, with Cameron Harris, and with Ijiju. The first and the last were students of mine, and Cameron was a mentee. They've all contributed very significantly to the material that I'm going to talk about, and I'd like to talk them up because they're all young and may need or maybe in a job search in the future. And if you see them, their names, you should know that they're really, really smart people. Okay, so I'm going to talk to you today about regular graphs, regular hypergraphs, and what I will define as the spectral gap in these structures. Sorry, let's see. Okay, oops, sorry. So the table of contents is as follows. First, I will give you an introduction where I will define all the quantities involved. I will give you a motivation. Why are we interested in studying these random objects? Then I will talk to you about their spectra, and I will offer a glimpse into the methods that we use to study this, because it's kind of an overview talk. I will tell you about a lot of results that exist in the literature, in addition to mentioning a work that I've done. And I'll draw some conclusions in the end, as one ought to do. Okay, so let me start with the notion of graph. Of course, everybody knows what a graph is, but let's fix some parameters that we will be talking about in this talk. So of course, there'll be a set of vertices and a set of edges. The graphs that I will be talking about here are going to be undirected, and they will have no loops. And mostly they will not have multiple edges either. So they will be simple graphs. As such, they can be bipartite, meaning that all the edges occur between two classes of vertices. So there's one class V1, there's another class V2, there's no overlap, and the edges only occur between these two classes. A graph can be regular, meaning that each vertex has the same number of incident edges. So the degree of each vertex is the same. And a graph can be bipartite, biregular, which is a combination of these two notions and an adaptation thereof as well, in the following sense. So we have these two classes, V1 and V2. They may have different numbers of vertices. So it may have n vertices in the first class, m vertices in the second. And all vertices in the first class have the same degree D1. All vertices in the second class have the same degree D2. And if you have seen these things before, you will immediately notice that in order for the number of edges to add up, we ought to have that n times D1 is equal to m times D2, which, as portrayed in this picture, means that if n is smaller, as I've tried to indicate through the fact that the oval on the left-hand side is a little bit smaller than the one on the right-hand side, then the degree of the vertices in it should be slightly larger to compensate. Okay. So why are we interested in graphs, and especially in random graphs? Well, graphs have been used to model networks of all kinds, from electrical to social and biological, for a while. And it turns out that random graphs allow us to study properties that most networks have in some sense. And they have also been shown to provide for good benchmarks for algorithms, for studying networks, for providing guarantees for such algorithms, and so on. They have so random graphs can have two desirable properties that real-life networks tend to share. So sparsity is one of them. And this makes a connection to statistical physics, where you can also study things like percolation and real-world networks in terms of sparsity, because as we know, in the real world, if you have a large network, the degree of a vertex tends not to be proportional to the number of vertices in the network. So it's much, much smaller than that. So we talk about such networks as being sparse. And the second property that they have that is desirable in the context of studying real-world networks is expansion characteristics, meaning that if you take a random walk on this network, then you're likely to lose yourself fairly quickly. You can start from a predicted vertex, but then after taking a certain relatively small number of steps in terms of the network size, you can be anywhere. So this talks about network connectivity, and the faster you lose yourself, the faster that the network mixes, the more connected it is. So these are things that we observe in the real world. You know, we all remember the 6 degrees of separation, 6 degrees of Kevin Bacon, and so on. So these are things that real world networks exhibit. Okay, so with this in mind, there are lots of applications for random graphs, starting with as I mentioned, electrical networks and social networks and biological. But nowadays, one of the main fields of study for random graphs is in data science or machine learning. Of course, data science is this kind of diffuse, amorphous field that encompasses a lot of areas of math, starting with probability, with linear algebra, with numerical analysis, with theoretical computer science, and all of this, statistics, not to mention combinatorics, random graph theory. So all of these things come together in the study of machine learning. And some of the topics where random graphs have been used recently are matrix completion, community detection, coding, recommender systems, bioinformatics, pattern recognition, and so on. So there's huge applicability for the study of random graphs, for the study of these expansion characteristics, and for using them for benchmarking and for providing guarantees for algorithms that are connected to machine learning problems. So let me tell you a little bit now about hypergraphs. Hypergraphs generalize graphs, of course, but instead of 2 vertex edges, pairs of vertices defining an edge, now we allow for larger subsets of vertices to form a hyperedge. So for example, here is an example of a hypergraph containing a variety of types of hyperedges. So for example, here, edge E4 contains a single vertex. You can think of this as a loop if you want. Edge E2, this orangish one here, contains 2 vertices, V2 and V3. So this is what we're used to as an edge in a graph, but it can also be seen as a hyperedge in a hypergraph. And then E1, this yellow edge here, and E3, the green one over here, each contain 3 vertices. So they are, you can think of them as triangles, if that makes more sense to you. But in either case, these are bona fide hyperedges. Okay, there are objects that we haven't seen before. So this is a representation of a hypergraph, and hypergraphs generalize graphs in very useful ways. So for example, here is a representation of a hypergraph that characterizes groups of students according to the course that they take together. So each one of these ellipses and circles denotes a hyperedge, and the depicted students included in it are vertices. So the hyperedges are subsets of students, And you can see that there's overlap. And you can see that the number of students in a class that share the same class can be different. And each one of these groups can be a hyperedge. Of course, we can use this kind of model to model a lot of structures, including co-authorship. We can certainly do that for social networks, but also for protein networks and so on. So it's just a more useful generalization of graphs that can adapt to model more complex relationships than just this simple edge which connects two vertices. Okay, oops, sorry. Okay, just like graphs, hypergraphs can have some attributes. So we talk about hypergraphs as being, again, simple. So we're talking about hyperedges being simple. We don't multiply them. We don't say that there are multiple hyperedges connecting the same set of vertices. In general, we think of them as having two or more vertices. So we ignore loops. So no multiple edges, no loops. And just like before, they can be, and this is actually a new concept, they can be uniform, meaning that each edge has the same number of vertices. Okay, so from this point of view, if you take k to be 2, so the number of vertices in an edge to be 2, then you recover graphs. If you take k to be 3, then you're going to have a hypergraph in which each edge or hyperedge is a triangle, and so on. So we will talk about such a hypergraph as being uniform. Every edge contains the same number of vertices. Let's turn that concept now on its head and talk about regular hypergraphs, also in the context of uniform hypergraphs. So they are regular if every vertex has the same number of hyperedges that it belongs to. So, for example, what's depicted here is a hypergraph in which each vertex has degree 2 and each edge contains 3 vertices. So in this notation, dk uniform hypergraph, this would be a 2-3 uniform hypergraph. So it's uniform and it's regular, and it has 6 edges and 9 vertices. Okay. Now, I talked about spectral gap, so that suggests the existence of a spectrum. So you might be familiar with the fact that graphs have a lot of a variety of matrices associated, to them. And so you can be comfortable talking about the spectrum of a graph, even though I haven't specified which matrix we'll be studying. But what about hypergraphs? Well, it turns out that any hypergraph also has a natural adjacency matrix. In fact, you can define a whole hierarchy of adjacency matrices for them, but there's one that's in particular very natural and turns out to be very useful. In addition to having adjacency matrices, hypergraphs also have a very useful operator associated to them, which is a tensor. Especially, or rather I should specify that if they are uniform, they have a tensor associated to it. So because you can think of a uniform hypergraph as essentially recording which k sets of vertices are included. And so you can construct a k tensor where, for entry I1, I2, Ik, it tells you if that particular k set is an edge or not, is a hyperedge or not. So it's a 0-1 thing. It'll turn out that even though both of these structures can encode various properties, it's easier to work with the adjacency matrix, in particular because there will be a very nice connection that one can draw to graphs. But more about that later. Oops, sorry, I keep on skipping too. Okay. So let me tell you just a little bit about what happens when we look at random regular graphs and hypergraphs, okay? Because these are the subjects of my talk today. So for graphs, I'm going to have two types of regular graphs that I'll be talking about. One of them is regular, and the other one is the bipartite biregular that I mentioned before. Sometimes this latter one is referred to as quasi-regular. Now, if the parameter is d, which is the degree of a regular graph, or d1 and d2, which represent the degrees of the two classes in a bipartite biregular graph, are fixed, then in practice, people work with multiple models for these graphs. The easiest one to work with, or rather the most desirable one, I suppose, is the uniform one, because this one just says, take one example, sample uniformly from the set of graphs with these properties and with fixed parameters, and then look at the properties of that object. But it's not so easy sometimes to work with such an object. In particular, it's very hard to sample from it because there are all sorts of restrictions, and it's not clear. I mean, there are algorithms who will do it, but they will not do it efficiently. And so instead, people work with things like permutation and configuration models, which, while not giving you even the same set of graphs, they can be shown to be contiguous to the uniform model, meaning that any event that happens with high probability in one of these three models will happen with high probability in all of them. So from this point of view, studying and understanding one of them is going to be sufficient for understanding all of them. So it doesn't matter which one you work with if you're interested in finding events that happen with high probability. However, if these degrees grow, then this contiguity is not known. And in fact, it's not clear. So there are some people believe that the contiguity can be shown differently than it has been done for the fixed models. And some of these models may still be contiguous even for the degrees growing, but nothing is known. So basically what we can do is just examine the uniform model, because the others will give rise to things like multiple edges and loops, and we don't really want to deal with those. Okay, so these are the models that we use.
Can I ask here?
Of course.
Is this that we don't know even if the degrees grow very slowly? There's no way.
As far as I know, this is not known, especially for the models that are used, like the configuration model, for example, is not known to work if the degrees grow.
Okay.
Van Woo thinks that it will, and who am I to argue with that? But there's no proof of that in the literature.
I see. Thank you.
Okay, so what about hypergraphs? For hypergraphs, we will talk about the uniform distribution about all possible, and we will talk about regular hypergraphs, so decay regular hypergraphs, and we'll talk about the uniform distribution amongst them, amongst all hypergraphs satisfying these properties, and with a fixed vertex set size. Okay, I mentioned already that there are lots of applications, both for graphs and hypergraphs. In particular, one of the hottest ones right now is in data science and machine learning, which is, for example, community detection. Community detection basically says, if I give you information about a network, can you tell me if it splits nicely into clusters that are highly connected and that are much less connected to each other than they are within themselves? So it turns out that for things like this, one important issue has to deal with the outlier eigenvalues and the existence of the spectral gap. So expansion is very important to such problems. Existence of expansion. Of course, expansion is being controlled by this spectral gap, which is the difference between the top eigenvalue and the second eigenvalue, or sometimes, depending on the complexity of the model, it may be that we want to have a set K of outlier eigenvalues that are well separated from the bulk of the rest of the eigenvalues and so on. So, but understanding this concept of what is an outlier, what it means for the rest of the eigenvalues to stick to the bulk, what the difference is between the top or the last, let's say, outlier eigenvalue and the bulk and so on. These are very important issues, and they have been used in all sorts of machine learning problems. And recently, even they're starting to be important for things like neural networks. So this is a newer application of spectral gap. Okay, so let me tell you about the spectra of these graphs and hypergraphs. For graphs, we will be interested in the adjacency matrix. Now, the reason why we've chosen this one and not any of the other matrices that you may have heard of, Laplacians and so on, is because for regular graphs, all matrices, Laplacians or adjacency, are equivalent. And the reason is the degrees are the same. So when you scale things or you subtract a multiple of the identity and so on, you do a very simple transformation of the eigenvalues, which will tell you that if there's if you know what the spectral gap is in one of these matrices, you can immediately compute what the spectral gap is in any of the others. So that's why it's sufficient to look at the adjacency matrices. Now, in general, adjacency matrices for random objects, for random matrices in particular, and for random graphs, even more in particular, I suppose, have been studied quite extensively. And many models of random graphs are just reducible to, in some sense, to random matrix theory, provided that the edges are independent. But in this case, for regular graphs, the edges are not independent because of the requirement that the degree is the same at every vertex. So there are some considerants that make this problem on the one hand slightly harder because you no longer have the edge independence to work with. But in a different sense, it's a much more rigid structure. And because of that, it has additional benefits. For example, even though a regular graph may be very sparse, if D is at least 3, then it will be almost surely connected, which is definitely not the case if you look at some other models, like, for example, Erdős-Renyi with an average degree of 3, even with an average degree of 100. Connectivity in such models will happen much later when the average degree becomes proportional to log n, so where n is the number of vertices. So very different properties. Now, for both the regular random graph and for the biregular bipartite random graph, the global shape of the spectrum has been studied since the 80s and 90s. For the former, it's known to be the Keston-McKay law. For the latter, it has been computed by Godzilla and Mohar. But outliers are a little bit more recent, particularly in the case of the biregular bipartite graph. So for the case of the irregular graphs with finite degree, well, in fact, in this case, D being finite doesn't matter. The largest eigenvalue is always D if the degree is D, and the corresponding eigenvector is all ones. But if D is finite, as the number of vertices goes to infinity, the asymptotic shape of the spectrum, or the limiting spectral density, empirical spectral density, if you know what that is given by this Keston-McKay distribution. And the support is between -2 root d minus 1 and 2 root d minus 1. As d goes to infinity, the Keston-McKay distribution converges to the semicircle density. But this is the case of taking a limit, not on d and n going together, but first on n and then on d. So there's no reason a priori to believe that if you take the limit in d and n at the same time, you will still get the semicircle density. And yet you do. I want to show you here, courtesy of Yufei Zhao, how this thing changes. So this is the Keston-McKay law and an empirical spectral distribution for some random deregular graph. You can see that here you get something that looks like an arc sign. And then as the degree grows, it flattens and then it expands in the middle. By D20, you can clearly see the shape of the semicircle happening. Okay, so this is how you evolve from Keston-McKay to the semicircle by taking this limit sequentially. Okay, so, but I mentioned the words shape of spectrum. It's a limiting object and it does not speak of outliers. So it only talks about what happens to the bulk of the eigenvalues. It says nothing about the eigenvalues, the outlier eigenvalues. For example, we know that there's always an outlier eigenvalue at D, outside, well outside of the spectrum. But the question is, what about other outliers? Can there be others? And the answer turns out to be no, but this answer was found in a sequence of papers starting with Alon Bopanna, who first showed that the second eigenvalue is bounded, or rather it cannot be lower than the bulk. Now this is a deterministic result. What I showed you before with the semicircle is true for the random deregular graph. So it happens with high probability. But this Alon Bopanna lower bound is deterministic. It happens for every graph. Okay, so it's slightly stronger than just saying, well, we can see that from the semicircle or from Keston-McKay and the location of the edges of the bulk there. So it's deterministic. Of course, they conjectured that this would be the case, that the upper bound would be the same. And this was indeed proved first by Joel Friedman, and then recently rediscovered by Charles Bordenave, who again was a speaker in this webinar. Recently, relatively recently, well, I say that, but it's been 6 years. And his method, which was using what at the time was something that was just emerging as a tool, a very useful tool for the study of spectral gap, is by now a very well established tool, and I'll say something about it later on. But they proved that essentially this second eigenvalue sticks to the edge of the bulk. Of course, this is true in the random case. And the reason for that is very simple. If you look at it deterministically, a deregular graph doesn't have to be connected. You can form it by taking two deregular graphs that are disconnected and putting them together, in which case lambda 2 is D again, because each of these two pieces will contribute their own D as an eigenvalue. So, but of course, such instances are exceedingly rare, and that is why for the randomly picked, uniformly randomly picked deregular graph, the second eigenvalue is going to stick to the bulk, to the edge of the bulk. So what this says is that almost all regular graphs are almost Ramanujan. A Ramanujan being a deregular graph for which lambda 2 is less than or equal, so where this little o of 1 disappears. That's what it means to be Ramanujan. And this is saying that almost all regular graphs are almost Ramanujan. Well, it turned out that very recently, Huang and Yao looked at the fluctuations at the edge of lambda 2. So lambda 2 minus 2 root d minus 1. They looked at the distribution of this quantity, and they found that they're polynomially small, and they showed a bunch of other results related to this. So this means that we understand pretty well what happens for deregular graphs, what the spectral gap is, and so on and so forth. It's a very well understood thing right now. But what happens if D grows? So for degrowing, until very recently, things were not so clear. For example, it was known that, again, so lambda 1 is D, lambda 2 was shown to be square root of D. So yes, there will be spectral gap. But the constant is not clear at all, because the bulk, the edges of the bulk are again going to be at roughly 2 root d minus 1, which, because d is growing, we can identify with 2 root d. But the constants that were obtained in this big O here were much, much larger than that. So it was not known to have this lambda to stick to the bulk, just that there is spectral gap. And there's a bunch of people who have studied these things, starting with methods pioneered, excuse me, by Kahn and Zim already, by Broder and his co-authors, and Cook, Johnson, and Goldstein showed that for d being no larger than n to the 2/3, we have this result that lambda 2 is big O of root d, and Tikhomirov and Youssef. Of course, Youssef, again, another person that, another very well-established author who gave a talk in your webinar, showed a sort of a complementary, slightly complementary regime where d has to be at least polynomial in n, but you can go with it up to n over 2. So this covered essentially, because n over 2, if you think about it, if you have a d regular graph, then its complement is going to be n minus d regular. And so you can just study what happens with d less than or equal to n over 2 by just changing some matrices. So this was enough. But it was conjectured, like I said, that this big constant present in O of square root of d, and we're talking things like 10,000, so really large constants, that this constant should have been 2, just like it is in the case when d is fixed. And it turned out that this conjecture was right, or at least now we know it for sure in this kind of the intersection of the two regimes that I spoke about before, which was d being no larger than n to the 2/3 and d being at least n to the epsilon. And it was proved in a paper by Bauer, Schmidt, Huang, Knowles, and Yao with the correct constant. So for this, we know now that it's 2 root d essentially. And by studying the fluctuations at the edge, they also showed that they are Tracy-Widom, for those of you who know what that is. They showed that for d large enough, a majority of regular graphs are actually Ramanujan, which is a very interesting concept, because Ramanujan graphs are very interesting from the fact that they describe quote unquote perfect expanders, and previous constructions of Ramanujan graphs were very difficult, were few and very difficult to do. So now we know that half of the graphs are Ramanujan, so it should be relatively easy to find one from by sampling, if we only knew how to sample uniformly distributed graphs for degrowing. Okay, so what's remaining to be settled? This conjecture is not known for d slowly growing, and it is also not known for d being very large, or in some sense very large, meaning greater than n to the 2/3. That means that the graphs are pretty dense. They're not quote unquote dense in the sense of dense random matrices where the number of entries, non-zero entries in each row is O of n, but they're pretty dense. So these are cases still remaining to be settled. What about the bipartite biregular graphs? Well, things are slightly more complicated here, because the bipartite biregular graphs have a symmetric spectrum, meaning that if lambda is an eigenvalue, then minus lambda is also an eigenvalue. In fact, this property of having a symmetric spectrum is characteristic of bipartite graphs. So if a graph has a symmetric spectrum, then it is bipartite. Now, their adjacency matrices are of this form. And for those of you well-versed in linear algebra, it should tell you immediately that there's a different problem than the eigenvalue problem that's related to this format of a matrix, and that is singular values. Okay, so if if we study eigenvalues for the irregular graphs, what we're essentially looking at here for bipartite graphs or for bipartite biregular graphs will be singular values of this matrix X, because the eigenvalues of this larger matrix are plus and minus the square roots of eigenvalues for XX transpose, which is, you should put you in the mind of Wishart problems. Of course, those are the singular values of X. So there's a lot of beautiful linear algebra associated to these bipartite graphs, and in particular to the bipartite biregular graphs that I'll be mentioning in a moment. Okay, so a BBG, which I'm using a shorthand for bipartite biregular graphs. And again, remember, we have two classes. We have 2 degrees, 1 per class. So such a graph has its largest or Perron-Frobenius eigenvalues at root d1, d2, and especially also at minus root d1, d2 because of this symmetric spectrum property. Okay, so we already know that there are 2 eigenvalues that will come out of the bulk, and we know where they're positioned. We know what their eigenvectors are. The question is, are they the only ones to separate from the bulk? First of all, how do we know that there is a bulk? Well, it turns out that this has been known for a while. So as n and m go to infinity proportionally, because as you might remember, even for the study of Wishart matrices, to obtain a limiting shape for the spectrum, you've got to take that the aspect ratio, the size of the ratio of the 2 matrix sizes has to converge. Otherwise, we can't talk about limiting shapes. But if we have that, then it turns out that it's known that the shape of the spectrum is known, and the edge, the right edge, is at square root of d1 minus 1 plus square root of d2 minus 1, and the left one will be at minus that, again, because of the symmetry of the spectrum. Now, you might see that both the result before with the largest eigenvalue and this one mimic exactly what happens in the deregular case if our bipartite biregular graph is actually a bipartite regular graph, meaning that the 2 classes have the same size and the graph is regular. Now, in and of itself, this was a surprising fact because the result known for deregular graphs was known with high probability. And the chances that a uniformly chosen deregular graph is also bipartite are exceedingly small. But it turns out that even on this exceedingly small set, you still have the properties that you expect to have. Okay, so as d1 and d2 grow to infinity proportionally, as the degrees go to infinity proportionally, you yield an analog of the Marchenko-Pastur law for Wishart matrices. Similarly, with the deregular case, one can establish a deterministic Alon-Bopana type inequality, saying that the 3-4 eigenvalues will either stick to the bulk or come out of it, deterministically this time. And with Herandi, Brito, and Cameron Harris, we were able to show that, in fact, the 3rd and 4th eigenvalue will stick to the edge of the bulk. So there will be no outliers for these bipartite biregular graphs with high probability as d1 and d2 are fixed and n and m go to infinity. Just the 2 Perron. Yes.
May I ask a question?
Please go ahead.
Basically, regarding the bipartite graphs, like how the issue of planarity, graph planarity, is involved. For example, the K22 is planar, but the K33 graph, bipartite graph, is non-planar. So any graph that contains a K33 or a K5 is
not planar, yes.
Correct. So how does that apply to this theory in particular?
Planarity has nothing to do with this.
No? Okay.
No.
That's good.
Yeah. As you know, well, let's see. Let me see if I can maybe clarify something. So planar graphs as we know, planar graphs have to have, if they're regular, they have to be of degree. So there's the degree 5 theorem, and in fact, we know that. So we don't have regular graphs that are planar beyond, I guess, 2, 2. And these results will be true for at least one of these D1 and D2 and so on, not 2. So bigger than 2. At least one of these has to be bigger than 2. And planarity is a property of the graph that does not translate into properties of the spectrum of the adjacency matrix. So this is, yeah, so they can be quite dense and therefore very much non-planar, but they will have this property. So the spectrum, the shape of the spectrum is known. Okay, so we were able, like I said, to show that the 3, 4 eigenvalues stick to the bulk, with the understanding that the 1 and 2 eigenvalues will be outside because the spectrum is symmetric. What about for growing degrees? Well, like before, it's not exceeding, I mean, okay, I shouldn't say that. It's actually quite technical, but it can be shown that if the degree is no larger than n to the 2/3, then the 3 and 4 eigenvalues are going to be proportional to root D1, which is the bigger of the two degrees. But of course, the conjecture is not that they will be proportional to, is that they will asymptotically be as large as the sum of the square roots of these two guys. Okay, so the actual constant shown here is pretty large, and this was done by Ijiju again. And this fact, this conjecture, was shown for a different model. So for a random sign model, meaning that you take the adjacency matrix of such a bipartite biregular graph, but then you multiply a plus or a minus 1 in each entry with equal probability. And if you do that, then you can show that these lambda 3, 4 do stick to the bulk. And exactly in this format as D1 and D2 grow. But for various reasons, that's a simpler model to work with. And this fact is not known for the actual graph adjacency matrix. So the problem is still quite open.
Ioana,
Yes.
by this process, do they alter anything else in the spectrum, or do the rest of the properties remain as well?
I think that the spectrum remains largely the same.
Okay.
Yes. But this is more or less it. So whether or not this process should alter the spectral gap, the initial knee-jerk reaction is to say it should, but we actually believe that it won't. The only problem is we don't know how to show that yet. So the problem is open. Okay, so let me tell you briefly what matrix we define for hypergraphs and why we can work with it. So for hypergraphs, we can define an adjacency matrix, which now is not going to be a 0-1 matrix anymore. What it will do is it's going to count the number of edges containing a pair of vertices ij. Of course, if it's a graph, then the number of edges is either 0 or 1, but here it could be many. Because remember, hyperedges are subsets of vertices, and there could be a lot of subsets of vertices containing this particular 2 pair. So it's no longer a 0-1 matrix. Now for k-uniform hypergraphs, instead of this matrix, you can define a tensor that contains complete information about the hypergraph. I should note that the adjacency matrix does not contain full information about the graph, because you can't necessarily reconstruct the graph from the adjacency matrix. You can from the tensor, but the tensor is much harder to work with, because even though we have now a good idea of what tensor eigenvalues ought to be like, the properties of tensor eigenvalues are not the same as for the for matrices, and so it's a more difficult problem to work with. Both the tensor and the adjacency matrix can be shown to be connected to expansion, but the matrix is easier to analyze, which is something that I've done with my student Ijiju in a paper from 2020, but also it can be shown to connect more directly to all sorts of expansion. Oops, sorry. I guess I deleted the bullet point that I had made for myself here, which was that there are multiple types of expansion, and the spectral gap connects to all of them, or rather relates to all of them. So rather than proving 3 different results, if you have knowledge about the spectral gap, you get all 3 of them at once. So it's a handy thing to have. Okay. So let me tell you a little bit about the spectral gap in regular uniform hypergraphs. So we look at DK uniform hypergraphs with n vertices, and A is the notation for the adjacency matrix here. Again, lambda 1 is known. The highest eigenvalue for this adjacency matrix is known. It mirrors exactly what happens in the graph case. The question is what happens with lambda 2. And this is something that's been studied. Again, a Lonbo-Pana deterministic lower bound was shown by Feng and Li. And for k equals 2, this is exactly the Lonbo-Pana case for, or rather, Lonbo-Pana lemma for the graph case. And you can think of the Ramanujan graphs, as I mentioned, as graphs that have the second eigenvalue less than or equal to 2 square roots of d minus 1. Of course, Feng and Li and Solé have then defined Ramanujan graphs, Ramanujan hypergraphs in a similar fashion. And they ask the question of, can we show that almost all hypergraphs, DK hypergraphs, are almost Ramanujan? There have been constructions of algebraic Ramanujan hypergraphs that have been easier or harder to actually build. And we were able to show through, or rather I'll say a few words if I have the time, that this is indeed the case, that the second eigenvalue, even for DK regular hypergraphs, sticks to the bulk with high probability as n goes to infinity. So it's the same thing. We only have the one Perron-Frobenius eigenvalue and no other outliers. Everything else is bulk and sticks to the bulk. Okay, so this is matching all of these bounds for graphs and for regular graphs and for bipartite biregular graphs. And it, like I mentioned, it connects to all 3 types of expansion, and it makes clear that the random walk on a DK regular hypergraph is going to mix fast, and it provides all sorts of other information that is useful in studying things like community detection. Okay, so let me give you a very quick idea of how you can look at such things, and how you can study spectral gaps. Suppose you want to look at the largest eigenvalue, and you want to bound the largest eigenvalue. So you want to look at the spectral radius of a matrix. Suppose that A is positive definite. You want to find an upper bound on the largest eigenvalue. You can use Gelfand's lemma. So you use the trace methods. You take the matrix power, you take some large power of the matrix, you look at the trace of that, and you take a 1 over mth power and you look at the asymptotics. M here being something that grows large, it'll grow large relative to n. This can be done, it has been done, it has to be done with a lot more care than things like showing the semicircle law via the moment method, which might be something that some of you are familiar with. But let's look at why this is not going to work very well on graphs. So for regular graphs, the largest eigenvalue is D, as I mentioned, and we want to look at the second one. Well, what I said before is a method for looking at the largest eigenvalue. So we're going to bring that second eigenvalue to first place by subtracting off, by projecting essentially in the direction of orthogonal to that eigenvalue, to the eigenvector corresponding to that eigenvalue. So if we look at this matrix instead, J here is the matrix of all ones. What we do is this matrix here will have one eigenvalue 0, and then the top eigenvalue will be lambda 2. So we can try and perform this sort of analysis on this matrix A tilde. But there's a problem with it. If we want to show that there's spectral gap, so we want to look at how large this trace of A tilde to the 2k is, we would like to show that in expectation at least is less than or equal to nd to the k. Because remember, so we want to show that the second eigenvalue is on the order of root d. So if we leave that to 2k, then we get d to the k, and we have about n of them. So we'd like to show something like this. Now, to absorb this n into the d to the k, because remember, we want to take a 1 over 2k power here to get eventually root d, we need to absorb that n into it. So we need k to be very large. We need, or sorry, not very large, but we need to grow at least like log n to get something meaningful. The problem is that this inequality as such, for k being that large, will be false. And the reason for that is that the probability of the graph, the deregular graph, becoming disconnected when is large enough. It's polynomially small, but it's large enough so that the addition of that second large eigenvalue, the second d eigenvalue, becomes to, or rather starts making a difference when k is that large, and is just going to make this inequality false. So this is not going to work. The adjacency matrix is not a good tool for when k grows to infinity in the deregular graph case. And so we must do something else. We need to change the matrix that we want to apply our trace method to. It turns out that the correct matrix, or rather, a much better matrix to work with in this case, is going to be the non-backtracking Hashimoto operator. And the reason for that is that we can connect the eigenvalues of this non-backtracking Hashimoto matrix to those of the adjacency matrix by the Harabas formula. So what is this non-backtracking matrix? Basically, instead of looking at indexing rows and columns by the vertices, we're going to index them by pairs of edges, pairs of ordered edges, namely pairs of edges that one can walk on in this direction. So like V's, right? But they have to be listed in the correct order in the graph. And moreover, they have to be true V's. They cannot be I's. You cannot walk there and back again. Okay, you have to go somewhere else. So this is what the non-backtracking matrix is. Turns out that there's this beautiful Harabas formula, like I said, connecting the spectrum of B to the spectrum of A. Here in this formula, D is the diagonal matrix of degrees. And so eigenvalues of B that are not plus and minus 1 are going to be eigenvalues of this quadratic pencil in A and D, essentially. And spectral gap for B will yield spectral gap for A and vice versa. But of course, the hard part is to show spectral gap for B. These ideas have been around for a while, and sometimes a self-avoiding matrix has been used. After Charles Bordenave used this non-backtracking operator to show spectral gap for deregular graphs in 2015, this method has been used extensively, both in the case of regular and quasi-regular graphs, but also recently in the case of independent edge ones under certain constraints of graph of degree concentration. It has been used for directed graphs. So it turns out to be really a gold mine, or rather a tool that you can really, really use successfully. So let me just show you very quickly what it can be used to show in the case of bipartite biregular graphs, which is where I've used it. Oops, sorry. So this is the formula again. And this is how eigenvalues are mapped. So if you can see here on the left-hand side, we have the positioning of the eigenvalues of the bipartite biregular graph adjacency matrix. So here we have adjacency matrix, here we have non-backtracking operator, and they're color coded. So things in the bulk, which I've denoted by green, get mapped on this disk here. Things that are larger and come outside the bulk on the right-hand side, so to speak. So in this yellowish green here and here will be mapped on the real line outside the disk. Things that are mapped on that are outside the bulk as well, but on the inner part, in these blue portions here, are going to be mapped on the imaginary axis outside the disk. And then the zero eigenvalues get mapped here and here, and potential zero eigenvalues that arise from the fact that the matrix X is not full rank get mapped here and here. And so if you look at this picture here, and you can show that the largest eigenvalue of a scaled version of the non-backtracking operator has all eigenvalues within the green portion. That means it has no yellow, no blue, and no pink. And so neither does this one. And this means that basically things stay inside the bulk and they stick inside the bulk, and there's no pink stuff. So the matrix X is not likely to be singular. Okay. So that's essentially what we did. I'm going to skip this because I'm really late. And basically, how do we map this thing to hypergraphs? Well, it turns out that, you think of DK regular hypergraphs, they should be similar to regular graphs. It turns out that intuition is wrong. They're not similar to deregular graphs. They are similar to DK bipartite biregular graphs. So that's why the emphasis on these bipartite biregular graphs, because they are the right object to study in the case of hypergraphs. And this bijection is very simple. So basically, remember this picture here where I showed you the 2-3 uniform regular hypergraph? Well, if you look at the set of vertices on one hand and the set of edges on the other, and you put an edge where a vertex belongs to one of the edges of the hypergraph, then what you get is a DK bipartite biregular graph. Okay, so this is almost a one-to-one correspondence, almost a bijection, except for the fact that you're not allowed to have a certain type of subgraph. So for example, here, I mentioned before that with the hypergraphs, we do not allow for repeated edges. So things like this cannot appear, where you have two distinct vertices here on the right that connect to the exact same set of vertices. You can't have that. But it turns out that this type of forbidden subgraph is really rare when you look at the uniformly chosen DK bipartite biregular graph. And so you can essentially ignore them. So if you look at the uniform measure on bipartite biregular graphs on this subset of not having certain subgraphs, things will be the same as for the entire set. You use the bijection to map that into the uniform measure on DK regular hypergraphs, and then you say, okay, therefore things will hold with high probability there. So this was a very neat thing, which allows us now to apply all the results known for random bipartite biregular graphs to DK regular hypergraphs. Okay, so I'm really exhausting my welcome here. So I'll just mention a few open problems and conclusions. So I mentioned various regimes that are still have questions that are open, both in the case of regular graphs and regular hypergraphs, because we can only translate results that we know for bipartite biregular graphs in this context for hypergraphs. And so if we don't have the results for BBGs, we can't have them for hypergraphs. So there's a lot of open problems. The non-backtracking operator, which is this new tool, or relatively new tool, that's been used very, very successfully for a variety of models, both regular and non-regular, is really something that you need to learn about and master if you want to understand spectral gap and proving spectral gap in such structures. And there's a keen interest in applications. And so this is a good area to work in, especially if you're a more junior person, a postdoc or a graduate student. There are lots of problems that are open. Things are very, very technical, but like most techniques, you can learn them. So there's a very fertile soil to be tilled here. And thank you very much for your attention.
Thank you very much for this very interesting talk. Are there any questions? Do you have some time for questions?
Yes.
Yeah, okay. Are there any questions?
Well, I have a question, just to comment on the largest eigenvalue and the Nonbacktracking. They're very good for computer vision or using neural networks. It's very similar. But I am more concerned about the simpler stuff, that the representation of the hypergraphs. Is anybody trying to use like a homomorphism into a set theory representation?
What kind of presentation? I'm so sorry, I can't.
I'm sorry, yes. A set theory representation where you can actually transform the hypergraph into a set theory notation for the purpose of, you know, maybe visualization. You can even, I guess you can work with.
So you'd like to see the hypergraphs in set theory notation? I have never looked at defining a spectrum that way.
And look, because it looks very clear that it's possible. I don't know, that the question is, and also it also looks clear that if you have cross products, you can actually represent it in tuples. And tuples are very good to write code in Python. So I don't know, this is very good for neural networks.
That sounds, yes, that sounds interesting. I have not seen this in the papers that I looked at that were doing spectral hypergraph theory. But I think, like I said, it's a very fertile problem, so or fertile area. So I would encourage you to look into that.
Any other questions or comments? If not, then let's thank Ioana again.
Thank you for having me.
Yeah. And may I wish you all a good winter break and holiday season, and we'll see you again in January. Thank you for attending, Paul.
Thank you for having me. Have a good winter break.
Thank you.